Okay, welcome back everybody. For this video, I'm going to be doing this practice final exam. Actually, it's a final exam from another class section from another year, so I'm just going to go through it. It covers pretty much everything. The one thing that's really not included in this exam, actually there's two things. This exam doesn't cover any material from 5.6 or 6.6, so that's average value and U substitution. Okay, so let's start. Okay, first problem. Worldwide wind energy generating capacity W was 42,300 megawatts in 2002, and it increased to 150,100 megawatts in 2009. Okay, so we let T be the years since 2000, and we're supposed to formulate a formula for W as a linear function of T, and then later as an exponential function, and then later as a power function. So let's start with the linear function. Well, we know we have kind of 2 points here, and the points are, well, 2002, T should be the years since 2000. 2002 means that T is going to be 2. And the height W of that point is going to be 42,300. And then the other point that we're going to have is going to be the point 9, 150,100. Okay, so I got my calculator here. The first thing I'm going to do, I want to find out what is y equals mx plus b. So first thing I want to do is compute the slope of this thing. I know m is going to be equal to 150,100 minus 42,300. That's y2 minus y1. And I'll divide that by 9 minus 2. That's x2 minus x1. So we'll get something divided by 7. Let's see what it is. 50,100 minus 42,300. You get 107,800. And divide that by 7. We get 15,400. So that's our slope. And now we could go one of two ways. We could try to plug one of these points in to the equation y equals 15,400. So this is way number 1. Plus b. X plus b, and then we would plug in one of these points. So we'll do the first point. It'll be 42,300 equals 15,400 times 2 plus b. So we will subtract 30,800 from both sides. And let's see what we get. Minus 11,500 is equal to b. Therefore, our equation is going to be y equals 15,400 x plus 11,500. So that was way number 1. Way number 2 is use y minus y1 equals m times x minus x1. So what we would do is just take one of these 2 points and plug it in for x1 and y1 in this equation, because we know that each of those points are on the line. So we'd replace m by 15,400, replace x1 by 2, and then y1 by 42,300 or something like that, and kind of ... get in a similar way to our final answer. Okay, so that's how we do a linear function from 2 points. Let's decide how we're going to do an exponential function. Well, if w is an exponential function of t and we have w of t is equal to w naught a to the power t, and these 2 points are still on our graph, maybe I can copy. Yeah, copy and paste. Look at that. So these 2 points are still on our function here. This is telling us that 42,300 is equal to, when we plug in 2 for t, so w naught a to the power 2. And we also know that 150,100 is equal to whatever w naught is times a to the power 9. Okay, so we're going to take these 2 equations and manipulate them in order to figure out what w naught and a are. Now I can see immediately, if I take these 2 equations on the right hand side, w naught a to the power 2 and w naught a to the power 9, what I want to consider really is how can I cancel one of these things in order to just have one variable? And the answer is 2. Well, since both terms have a w naught present, then what I can do is divide these 2 terms and the w naught will go away and I'll just be left with some power of a. And if I divide the right hand sides, I can just divide the left hand sides. So let's do that. We'll take the bottom one and divide it by the top. So we'll get w naught a to the power 9 divided by w naught a to the power 2 is going to be equal to 150,100 divided by 42,300. Okay, so let's divide those things. 150,100 divided by 42,300 is probably 3.5, yeah. So 3.54846 ... I would say on your exam, take it out a few decimal places. You don't have to take it all the way out, all 9 decimal places or whatever. But just take it out a few and try to make it relatively accurate. Okay, so now what we're going to do is just cancel some stuff. Well, w naught divided by w naught is just 1, and then we have a to the power 9 divided by a to the power 2. The way we do that one is by subtracting the powers. So we're going to get a to the power 7 equals 3.5486 ... And then we're going to compute a by taking the 7th root of this thing. And taking the 7th root, 846, I'm missing a 4. Amounts to taking the 1/7 power So I'll take this number here and I will raise it to the power 1/7. And if I do that, I get 1.198333209. Okay, so that's my A. which is great because now I know one of the two things which I didn't know before. I need to figure out what A is, and I need to figure out what W naught is. Well, I can rewrite each of these equations here. Well, I'll just rewrite one of them. I'll rewrite the top one as 42,300 is equal to W naught times, I'm going to replace A by the thing that we just figured out A was, 1.19833,209, and that's to the power 2. So all I have to do to figure out W naught is divide both sides by this thing here. So 42,300 divided by 1.19833,209 squared. So I'll take that number and square it, and then I will take 42,300 divided by that answer, and we get 29,456.2868. Okay, so that's how we can do this problem. Great. So let's see here. Next up, we want to write W as a power function of T. So we didn't actually do any problems like this in our class, but I like it. It's a good problem, and it's worth learning how to do. I could test on it, but here's what I would say. Learning how to do this problem is really sort of a culmination of understanding the definition of a power function and this principle, which we already just applied, actually. So I do feel like this is well within the grasp of the class. So here's how we would do it. We're going to use the exact same method that we used up here. So we're going to have 42,300 is going to be equal to, now I know that T should be 2, so I'm going to say K times 2 to the power P, and 150,100 is going to be equal to K times 9 to the power P. And these are going to be my two governing equations. And so first of all, I kind of want to figure out, I want to figure out what K and P are. And so my initial thought here is to try to use the same method that we just used before to get rid of the K. So I'm going to take these two equations and divide them again. And what I'm going to get is K times 9 to the power P over K times 2 to the power P. Well, those K's are going to cancel, and we will get 9 to the P over 2 to the P, which is the same as 9 halves to the power P, which is the same as 4.5 to the power P. And that's all equal to, well, K times 9 to the P was 150,100 divided by 42,300. And we said before that that's 3.54846. Dot dot dot. Okay, and what we're interested in knowing is really what is this P, this power P? This is what we want to find out. So we have an equation, 4.5 to the power P equals some number, and we want to know what the exponent is. So this should be screaming out for a natural log on both sides. So let's do it. We'll get ln of 4.5 to the power P is equal to ln of 3.54846. And then we can rewrite this left-hand side as P times ln of 4.5 using the logarithm rule, the power rule. And now we can divide both sides by ln of 4.5. and we get P is equal to ln of 3.54846 over ln of 4.5. So let's see what we get when we do that. 54846. Take the natural log of that, divided by parentheses 4.5 ln in parentheses equals, I'm getting 0.84205 dot dot dot. Okay, so I found out what P is. I should move all of this over a little bit so I can have some room. The last step now is to take P again and plug it into one of our equations. So we know that 42,300 equals K times 2 to the power 0.84205. So we'll take K to be equal to 42,300 divided by 2 to the power 0.8405. 84205. Okay, so 2 to the power, previous answer. Now we take 42,300 and divide by that. Getting 23,597.01083. Okay, and well, I haven't been a very good student, because what I should have done at the end of each of these problems is written the equation that it should be. For this one, it was W of t should be equal to, we decided W naught is 29,456.82868, and we should multiply that times A, which we decided is 1.1983329 to the power t. And on this one here, we should get W of t equals 23,597.01083, that's our k, times t to the power p, where p is 0.84205. Okay, so the only thing that we really used to compute the answer to this problem was our understanding of the form of a power function, okay, which means we have some constant k times the variable to some power p, where p is some real number that's not zero. Okay, real number that's not zero. Okay. Cool, so let's move on to the next problem. Okay, so we have some table here which is telling us the net sales in millions of dollars of the gap at some time t, where t ranges from being 2005 to being 2010. And each year we have a certain number of sales going on in that year. And what we're supposed to find is the average rate of change in net sales between 2005 and 2010. And remember, the average rate of change is going to be given by the formula f of b minus f of a over b minus a. So we can go ahead and compute that for this problem. It's going to be f of, well, actually for us it's going to be s of 2010 minus s of 2005. and then we're going to divide by the difference in those years, 2010 minus 2005. And so that's going to be 14,660. And we will subtract 16,019. And we'll divide that number by 5. And we get negative 271.8. Okay, so what that really means in terms of the problem is that between 2005 and 2010, sales decreased on average 271.8 sales per year. Okay, that's what this is saying. Okay, so this is going to be sales per year. No, it should be sales in terms of millions of dollars per year. S is in millions of dollars. So we should have our sales decreased on average $271.8 million per year. $1 million per year. Okay. So now we want to estimate Dsdt at time t equals 2008. So what we really have here is like a graph of some very incomplete data set. We know here's 2005. We've got 6, 7, 8, 9, and 10. And we go 16,000 and then like something smaller and then smaller again and then smaller again and then smaller again and smaller. No, we raised for the last one. Okay, so this is kind of what our data set looks like, and what we're trying to do is understand the rate at which sales are changing at t equals 2008. So 6, 7, and 2008 is right here. So what's going to happen is we're going to take a look at this point right here, and we want to know how the function is changing at this point. The sad fact of things, though, is we don't really know what this function might look like. It could be something crazy like this. Okay, but if we assume that it's not too crazy, then we can sort of expect the rate of change at this point to be similar to the rates of change at between these two lines. So line number 1 comes in the direction of the next point, and line number 2 goes in the direction of the other point. So if we take the average of these two slopes of these lines, then, okay, let's say S itself looks something like this. Then the slope of the tangent line to S at this point is going to be similar to the slope of these two purple and red lines. Okay, so what I'm actually going to do is compute the average rate of change which passes through the 2 points which are sort of next to our actual point, And we're going to say that the slope of the blue line is going to be not too different from this line, which is sort of connecting these 2 points which are to either side of our point of interest. Okay, so what I'm really going to do here is to compute, well, to estimate Dsdt at t equals 2008, take average rate of change of S on the interval 2007 to 2009. And that's going to be equal to 14,197 minus 15,763 divided by 2. So let's use the calculator. Minus 15,753 divided by 2, and we get negative 783. Okay, so that's how we do that. Great. All right. Yeah, 2. Okay. So that's how we can estimate that Dsdt. So that's one technique we learned in this class. So let's see. Number 3, we have a t-shirt seller. Needs $400 to start up a website. The t-shirt seller buys t-shirts for $12 each and sells them for $30 each. So we're supposed to find the cost and revenue functions. Well, first of all, we know that the cost function, C of t, is going to be equal to the fixed cost plus the variable cost. In our case, the fixed cost is taking the form of this $400 that we need to start up the website. And the variable cost is going to be the expense which we're spending to buy the t-shirts ourselves. So we buy the t-shirts for $12, and you can tell it's the variable cost because of this word right here, each, meaning that the amount of money I spend on t-shirts depends on the number of t-shirts that I buy. Hence, it is variable. So this is going to be equal to $400 plus our variable cost will be $12 per t-shirt. So if t is the number of t-shirts, we will put t. Why don't we make it q? We'll make it q. This is the usual notation that we've used in this class. We use q for quantity of t-shirts. 12q. Okay, and then the revenue function, r of q. Well, the only revenue we're going to get is going to be variable in a sense, right? Because revenue is going to be strictly tied to the number of t-shirts that we're selling, and it's going to correspond to the amount of money which we are selling. It's going to be equal to 30q. Okay, so we have our cost function, we have our revenue function, and now we can go ahead and answer part B, which is asking us how many t-shirts do we need to sell in order to make a profit. Well, if we're going to talk about profit, why don't we write down what the profit function is? We know that P of Q is going to be equal to R of Q minus C of Q. Okay, so we take the revenue that we make and we subtract from that our costs, and that's how we figure out how much money we made. And in our case, this is going to be this is going to be 30q plus minus 400 plus 12q in parentheses, because remember, we want to subtract the entire cost function. So we will get 18q minus 400. as our profit function. Now, what does this look like? You know, P of Q is 18Q minus 400. That looks like a linear function to me. In fact, it looks like a linear function which starts down at negative 400, and it rises with a slope of 18, and goes up like this, and that's our profit function. And what we want to find is how many t-shirts do we have to sell in order to make a profit? And we can take a look at this graph and kind of decide what condition we're really going to need to meet in order for this to happen. Well, if we take a look at this graph here, we can consider the profit as being, well, first we're losing money, and we produce more and more goods, and our loss becomes less and less and less, until we get to a point where if we sell more than a certain amount, we're going to start making money. So making money is pink in this problem. Okay, so the point we're really interested in finding is this point right here. Right? This point right here where profits go from being negative to then being positive. And that is a horizontal intercept. Okay? It's the place where the height of the function is equal to 0. So at this point here, we know that we have, if this is the point, why don't we call it, it's the break-even point, so we'll call it B. We know that P of B is equal to 0. And we're interested in knowing what is this value Q equals B. Okay, so what we want to do is set this equal to 0. So we'll take P of B equals 18B minus 400, and we set that equal to 0. So 18B is equal to 400. So B is equal to 400 divided by 18 equals 22.22. Okay, so what is this saying? This is saying if we produce 22.22 shirts, then we will start making profit. That is the point where profit and costs, or revenue and cost, are exactly equal to one another, and our profit is 0. So if the question asks us how many t-shirts should we produce in order to make a profit, well, we should talk about what is the first t-shirt produced which produces a profit. And the question is, well, should it be 22 or 23? Well, if we produce 22, then the Q value is going to be slightly to the left of this break-even point. So 22 is like right here. And 23 is going to be right here. Well, if we choose 22, we're going to lose money because we have this value here which is beneath the x-axis still. If we choose 23, we'll be slightly above. So a good answer to this question would be 23. All right, wonderful. So number 4, we got a radioactive substance, and the atoms are decaying into more stable atoms, and we're talking about radon here, which has a continuous decay rate of 18% per day. And we're supposed to find the half-life of radon. Okay? And the interesting thing about half-life is it is an amount of time for any amount of radon to diminish to half of the original amount. Okay? So in particular, we're not really worried about how much we originally have. Okay? We'll have something like 1 kg of radon will decay to half a kilogram in the same amount of time that it takes half a kilogram to decay to a quarter of a kilogram. Same time. So we know that we can measure the amount of radioactive substance left using a continuous decay model. Okay? Since continuous decay, we know we should use the equation P equals to, why don't we say P of t is equal to P naught, that's our original amount, times e to the, now I need to consider this rate here, it's a decay of 18%, and it's a continuous decay, which means that we should use the E model, and we should have k is equal to negative 0.18. So negative 0.18 t. Okay, and what we want to do now is find the value t, which will cause the left-hand side to be half of our original value. Well, if our original value is P naught, so we have some quantity of radon, and we have half of it left, well, what we really are interested in is the equation where we have 1/2 of P naught on the left-hand side, and on the right-hand side we have P naught e to the negative 0.18 t, and we want to solve this equation for t. So we can cancel our P naughts, and then we have 1/2 equals e to the negative 0.18 t. I'm really interested in this value of this power here, and I need to get it out. The way we get things out of the power is using a natural log, so I'll take the natural log of both sides, and I will get ln of e to the negative 0.18 t. Now if you watch the other video on what to know for the exam, you'll know that ln and e are inverses of one another, and if I take ln of e to some number, I'm just going to get that number. So I can simplify the right-hand side to be just negative 0.18 t. Finally, to find t, I just divide both sides by negative 0.18, and I get ln of 1/2, and I divide by negative 0.18, and I get, let's see what I get. And divide by negative 0.18. I get 3.8508. And would you look at that, it actually is true that the half-life of radon is 3.8 days. Wonderful. Okay. Yeah, finally, we should make sure to note what are the units of T. And since our continuous decay rate is measured daily, we know that this should have the units 3.8508 days. Okay, so don't forget to have units on your answers. Okay. So now we're going to do this problem concerning the weight of a child. It's a function of its age A in years, so that W is equal to F of A. And what we're supposed to do is take this information about the function and really the connection between the function to the real world and interpret these statements about the function to represent statements about the real world. So we know that f of 7 is equal to 85, so 7 is our value of A here, and 85 is our value of W. So this is to say that the age of the child is 7 and their weight is 85 pounds. So is it a specific child? I guess it is. The child weighs 85 pounds at age 7. And next we're supposed to interpret some statement about the derivative of the function f. So we have f prime of 7 is equal to 6. So what this is telling us is that the age of the child is still equal to 7. And this value 6 is representing the derivative of f prime, which is telling us how is w changing with respect to time. Which is to say that this is the rate at which the child's weight is changing when the child is 7 years old. So when the child is 7 years old, their weight is, and here I can put something like increasing at a certain rate or decreasing at a certain rate. Since I found that the derivative is a positive number greater than 0, I'm going to use the word increasing at a rate of, and now I'm going to write down the rate. It should be 6 pounds per year. And the way I know what the units are is by considering this fraction here, dw dt. dw is going to be a change in weight, and the bottom is going to be a change in time, where, oh man, I guess it should have been a dw dA. Should have dw dA. So the top here is going to be a change in weight, and the bottom is going to be a change in age in terms of years. So I just took the pounds per year to correspond to the units of this fraction. Okay. Let's see. So, part C, we want to use this information to estimate how much a 10-year-old weighs. Okay, so what is the information we have? We know f of 7 and f prime of 7. We want to know what is f of 10. And this problem is screaming out for tangent line approximation, because we don't know anything else about the function f other than the value of it at a point and the value of its derivative at a point. And those two things uniquely determine the tangent line of the function. Okay? So what we really know is just that at 7 we have a certain height and we have a certain direction. And we have no clue what the actual function looks like. It could be very crazy. We don't know what it looks like. But what we do know is that the value 10 is not too far away from the value 7. So what we can do is just estimate the purple value by the pink value. So that's what we're going to do. So if you don't remember, the tangent line approximation formula is that the tangent line is going to be equal to f of a plus f prime of a times x minus 7. And here a nicely corresponds to the actual value a, which we're going to be using here is going to be 7. So we're going to get f of 7 plus f prime of 7, that should have been an a in here, x minus a, times x minus 7, which is equal to, well, f of 7 was 85, plus 6 times x minus 7, and we're interested in knowing what is f of 10? Well, f of 10 is going to be approximately equal to t of 10, which is going to be exactly equal to 85 plus 6 times 10 minus 7, which is 85. Oh. It's going to be 85 plus 6 times 3 is 18, which is like 103. And yeah, that's our approximation. Okay. So next problem, we just have a straight up derivative to take here. We want to find the derivative of this function z, which is a function of t. So I'm going to write it using Leibniz notation. We'll write Dsdt. And what we need to now do is the derivative of cube root of t squared plus 7 with respect to t. I'm going to rewrite that inside as a power. I'm going to write t squared plus 7 to the power 1/3. And I'm going to apply a couple rules here. First of all, chain rule. I have a function inside a function. The inner function is t squared plus 7 to the 1/3, or t squared plus 7, and then the outer function is like z to the 1/3. Or we shouldn't use z, we should use y or x or something. Z is already tied up in the problem. So we should use chain rule, and I'm also going to need to use power rule, and I'm going to need to use constant rule, derivative of a constant. And I think that's it. I'm going to have to use power rule twice. Okay, so the first thing to do is derivative of the outside function, where we leave the inside alone. So we'll leave t squared plus 7 alone. And if we want to do its derivative of the outside function, well, it's just z to the 1/3, or x to the 1/3, or y to the 1/3. So we just use the power rule. The power should decrease by 1. 1/3 minus 1 is negative 2/3. And we should multiply out front by the old power. Finally, we need to chain rule out the derivative of the inside, which is 2t. And that is how we find dz dt. I suppose you could write this in a slightly more concise way, maybe 2t over 3 times the cube root of t squared plus 7 squared, something like that. But you can just leave it like this on your exam, and I'll accept that. Okay. Now we need to find the derivative of this problem here. Q of r, we'll use Newton's notation this time. And we have, it's kind of convenient that they wrote this as Q of r, because Q of r could easily stand for quotient, which is the rule that we're going to have to use here. Well, not have to. If you want, you can use product rule. If you stayed after class that one day and learned how to never use quotient rule. If you go to the video on quotient rule, it's at the end of the video. You can learn how to not have to memorize quotient rule, but we're going to use it here. So what is it? Well, I know that the derivative of f over g is going to be equal to g f prime. That's low d high minus high d low, all divided by low squared. So gf prime minus fg prime over g squared, where in our case f is equal to r plus e to the 5r, g is equal to 4r minus 2r cubed, and computing their derivatives is relatively straightforward. We're going to get 1 plus e to the 5r times 5, and g prime will be 4 minus 6r squared. So combining all of this stuff, we get g times f prime. We're just going to crisscross applesauce these guys. For the top, g f prime is going to be 4r minus 2r cubed. Multiply that by 1 plus 5e to the 5r. We will subtract from that. We'll do f times g now. G prime. Divide by g of x squared. And that's my final answer. If you're really dedicated, you can FOIL all of that stuff out and simplify to the best of your ability, but I feel like this is a good stopping point, especially for the purposes of review. Okay, I'll be right back. I'm gonna grab a drink of water. Okay, I've been talking for like 2 hours straight with the other video. Okay, so find the inflection points of y equals x e to the x. Okay, so I know that the definition of an inflection point is when f double prime changes sign. Okay, so we know that this is when f double prime changes sign, and we know that f double prime can't go from being negative to being positive without crossing the 0 point, right? So we want to find candidates for f double prime, and these candidates are going to be any point where maybe f double prime becomes 0. And we'll have two kind of scenarios here. We can have a situation where we pass through, or we can have a situation where we come up and hit 0 just for a second and then go back down. Okay, so if this is the graph of f double prime, then this value will correspond to an inflection point. Well, this value here is not going to be an inflection point. So let's start by finding the candidates. So the candidates will be when f double prime equals 0. So first of all, let's compute f prime of x. That's going to be, we're going to have to use the product rule on x e to the x. So the first one will be x times the derivative of e to the x, which is just e to the x. And the second one will be 1, the derivative of x, times e to the x. So we get x e to the x plus e to the x. And then f double prime of x should be equal to the derivative of the derivative. So we'll take x e to the x plus e to the x and take its derivative. For the first term, we use the product rule again. X e to the x plus 1 e to the x plus the derivative of e to the x is e to the x. So we get x e to the x plus 2 e to the x equals 0. This is what we want for a candidate. So if we want that to be equal to 0, let's just solve it. We'll take x e to the x on one side, and we will set it equal to 2e to the x on the other side, negative 2e to the x. And we can cancel the e to the x on both sides, and we'll get x equals to negative 2. Now we have found a candidate for an inflection point. What we need to do is verify whether or not f double prime changes sign at this point. So what we're going to do is create a number line. I'm going to put negative 2 on here, and the number line should tell us the sign of f double prime of x, because we want to say whether the sign is going from negative to positive or positive to negative, or not doing either of those things. So I want to know what the value of the sign is on each of these two sides of this point here. So the first one I'm going to do will be, I'll take negative 3, and I want to plug in an easy point to figure out on the right hand side. I'm going to take 0. Okay, so if I plug in f double prime of negative 3, I get negative 3 e to the negative 3 plus 2 e to the negative 3, which is equal to negative e to the negative 3, which is less than 0, because e to the negative 3, e to the x is always a positive number, no matter what we plug in, and if we take negative of it, we're going to get a negative number. Okay, so we have less than 0 in this interval here. And then after negative 2, let's try f double prime of 0. Well, it's going to be equal to just 0 times e to the 0 is 0, and then we'll have 2 times e to the 0 is 1. So this will be 2, and that is larger than 0. So we have verified that f double prime went from being negative to being positive, therefore we have an inflection point. So we have an inflection point at, and what we should write now is the ordered pair, which corresponds to the x value negative 2. We'll have negative 2, and then f of x is x e to the x, so negative 2 e to the negative 2. That is where we have our inflection point. And we can say with confidence that there are no other inflection points on this graph on account of the fact that f double prime has to be equal to 0 at an inflection point, and we found the only place where that is true and tested it and found an inflection point. Since there are no other places which were candidates, we can say with authority that there are no other places where we will have an inflection point, because how can you have an inflection point without it being a candidate first? Okay. Number 8 here. How many of these do we have? Oh, geez, okay. Okay, number 8. Ball is tossed straight up with an initial velocity of 50 feet per second. The ball is 5 feet above the ground when it is released. Its height in feet at time t seconds is given by this function h. And we want to know, when does the ball reach the highest distance above the ground? Alright, so h is going to be a parabola, and it's opening down because I have a negative number attached to the quadratic term. So it should open down, and our height of our function here is measuring the height of the ball. So I know that the point where the ball is going to be highest above the ground is going to be this point right here, where we reach the maximum. And that point satisfies two things. First of all, it's the vertex of the parabola. And second of all, it satisfies another property, which is that the tangent line is negative. Or not negative. The tangent line is horizontal. So you can use techniques that you learned in algebra to find the vertex of h of t. I'm going to use the second method where I'm going to find the point where the tangent line should be horizontal. I know that the slope of the tangent line is h prime of t equals to, I'm going to compute the derivative, take the 2 down, we get negative 32t plus 50. I know that that should be 0. So t should be 50 over negative 50 over negative 32, which is equal to just 50 over 32. Okay, so this is the time when the ball reaches the highest distance above the ground. If we want to know the height that we reach at that particular time, we should take this time and plug it into the original height function and get h of 50 over 32 equals, so this is seconds, and h of 50 over 32 should be negative 16 times 50 over 32 squared plus 50 times 50 over 2 plus 5, and that's going to be measured in feet. Okay, so that's how we would sort of use our more calculus techniques to do this problem, although you don't really need calculus to do this problem. Oof, this is going to be a long one. Okay, better add a page in here. Okay, so we have some function x squared plus 2 dx, and we want to use a left-hand sum with 6 rectangles. No, with rectangles with width 6. So if we have each rectangle is 6 units wide, then we can use the equation delta t equals b minus a over n to figure out what n should be, because we know that b and a are 18 and 0, so we have 6 is equal to 18 minus 0 over n. This means that n should be 3. So we should have 3 rectangles, and we should use a left-hand sum. And we're supposed to sketch a graph and shade the rectangles used for this approximation. So let's do the graph first. And what does this function look like? Well, it's just a parabola opening up, and it is a little bit off the ground. So here's 2, and it's a parabola opening up. And if here's 18, we are trying to estimate this kind of salmon-colored area here. This is the area that we are trying to estimate. And we're going to use 3 rectangles. So let's make some markings. Each of them should basically take up a third of our domain, which goes from 0 to 18. So 6 here, and then 12 here. And we're using a left-hand sum, okay? Left-hand sum means we take the height of each rectangle to be the height of the function on the left side of the interval. So in our case, we're going to take this point, which is on the left-hand side of our first interval, and we are going to extend it. We're going to compute this area. And we're going to take the height on the left side of the next interval and extend it. Finally, the last interval. So we're going to try to approximate the area of this salmon region by the area of the red boxes, add it all up together. So I know that this is going to take the form of the following. The area is going to be approximately equal to the area of these red boxes. The area of the first box will be, is our function f? F of x, yeah. F of 0, that's the height on the left side of the interval, times the width of the interval, which is 6. We add to that the area of the second box, f of 6 times 6, and we add to that the area of the final box, f of 12 times 6. So this will be equal to 6 times, we're going to add f of 0 plus f of 6 plus f of 12. Well, f of 0 will be 2. F of 6 will be 36 plus 2. And f of 12 will be 144 plus 2. Six times 186 equals 11,000 or 1,116. Okay, so there was one tricky thing about this, which was that rather than telling us how many rectangles we were supposed to use, they told us what the width of each rectangle should be, which implicitly defined the number of rectangles which we are using because of this formula delta t equals b minus a over n. Usually they give us b and a and n and ask us to figure out what delta t is. In this case, we had to figure out what n was, which is really just for the purposes of making the drawing. Okay, so that's how we do that one. I guess I didn't need this extra page after all. All right. One stock of Google Inc. is currently worth $5.50, and its price is increasing at a rate of a certain number of dollars per month. And we're supposed to figure out how much the stock will be worth 1 year from now. Well, this problem is ambiguous. The problem is ambiguous. And I'm gonna I'm going to take a guess at what the author had in mind. I think what they meant to say was increasing by a factor of e to 0.01 t dollars per month. That would mean that we have a continuous growth, exponential growth model. So we're going to use the equation P of t equals P naught e to the kt, where k is given to us, it's 0.01. And P naught is just going to be the current worth. So P of t is going to be 550 e to the 0.01 t. Now, one thing we have to be a little bit careful about is that the problem tells us that we are increasing by this factor on a monthly basis. And we are asked to answer the question, how much will the stock be worth 1 year from now? Which means we're interested in knowing what is P of 12. Well, it will be equal to 550 times e to the 0.01 times 12. So, well, let's simplify first. We got e to the 0.12. And if we take e to that value, we get 1.12 something multiplied by 550. We get $620 and 12 cents. And I'm going to write approximately equal to, because there's a little bit of decimals beyond this. But it's good to cut off your decimal points at the hundredth place when you're talking about money, because we don't really typically talk about fractional cents when we're doing finance. Okay, so that's that problem. And now we have this next problem, pretty standard integration here. We want to find the indefinite integral. We've got 2x to the 5th plus 3 over x minus 7e to the 4x. First things first, I'm going to use the constant rule and the sum rule to split this up. 2 times the integral of x to the 5th dx plus 3 times the integral of 1 over x dx minus 7 times the integral of e to the 4x dx. And now each of these looks like something I know how to do. I have a rule for how to do 1 over x, I have a rule for how to do x to the 5th, and I have a rule for how to do e to the kx, where k is some number, in our case, k is 4. So I'm just going to write 2. I'm going to write now the antiderivative of x to the 5th. We raise the power by 1 and divide by the new power. Now I add to that 3 times the antiderivative of 1 over x is ln of the absolute value of x. And I'll subtract 7 times the antiderivative of e to the 4x, which will be e to the 4x divided by 4. And to all of this, I will add my constant c. Okay, since I did an indefinite integral, the result of my work should ultimately be a family of functions. Okay, it's the family of functions of the form 2x to the 6th over 6 plus 3 ln absolute value of x minus 7 e to the 4x over 4 plus some number. That's a pretty standard problem there. Okay, cool. Now we get some rapid fire multiple choice problems. We have these things here. So okay, we wanna find the y-intercept of the line 3x plus y equals 24. And what we should be really careful about is that a y-intercept is going to be the point where the function crosses the y-axis. So it's going to be this red point, and this red point has the form 0, comma something. We're interested in knowing what the point is. So in particular, a y-intercept is going to occur when the x value is equal to 0. So if we have this equation here, we can just replace x by 0. We get 3 times 0 plus 4y equals 24. Therefore, y equals 24 over 4 equals 6. So, our answer is D. I guarantee you that when this test was given, probably, well, I won't guesstimate, but I will say I would expect a lot of students to make a mistake here where they say that y-intercept means the y value should be 0. That's not true. If the y value is 0, then we have a horizontal intercept. The x value is 0, then we have a vertical intercept. Okay, number 13, a quantity changed from 12 to 9. What is the relative change in the quantity? This is a pretty straightforward question. Relative change is given by the formula x2 minus x1 over x1. In our case, 19 minus 12 over 12. So that's going to be 7 over 12, which is 58.3%. Okay, a product costs $40 today. Its cost is decreasing at a rate of $2 per day, and we want to find the equation which represents the cost of this product t days from now. Okay. Well, $2 per day is a constant rate of change. $2 per day every single day. The rate of change is constant. The type of function which has a constant rate of change is a linear function. So we can immediately discard C and D as possibilities. Okay. Now the question is, should we have 40 minus 2t or should we have 40t minus 2t? And I like the first answer, or 40t minus 2. I like the first answer better because this is saying that on the first day when t is equal to 0, this term just goes away and we're left with just $40. And that verifies our situation where we have our product costing $40 today. Whereas the other one, if we plug in t equals 0, so today, then this will go away and we'll have c of 0 is equal to -2. That would mean that the product is worth -$2 today, which doesn't correspond with our problem. So I'm going to say no to B and yes to A. Okay, now we have a product which costs $40 today and its cost is decreasing at a rate of 2% per day. So which equation represents the cost of this product t days from now? Since we know that we're decreasing at a rate of 2% per day, this is a variable rate of change, okay? So the rate of change is not constant, which means that I can eliminate any linear equations as possibilities. Now the question is, should we have C or D here? And the answer really comes down to this value which is inside our parentheses here, 0.98 versus 1.02. Well, 2% is initially making me think, okay, 1.02, yeah, 2% and 1.02 make sense together. Those look like the same number. But this is tricky, okay? This is tricky because the cost is decreasing at a rate of 2% per day, which means that R is equal to negative 0.02, which means that A should be equal to 1 plus R, which is negative 0.02, which means that A should be equal to 0.98. So we should choose D and not C. You can also figure this out relatively quickly if you just plug in some random value of t. Say, take a look at 5 days from now. So you plug in 5 for t, do 1.02 to the power of 5 times 40, you're going to get a number which is bigger than what you started with. And that doesn't make sense if our cost is decreasing. Okay, 16. We have cost and revenue of producing Q units graphed below. So what production level maximizes profit? Well, remember, when we have a revenue function and a cost function, if the cost is bigger than our revenue, then we're losing money. So these places are going to be where we're losing money. And if the revenue is bigger, then we're going to be gaining money, and that's going to be like profit. And the bigger our green line is, the better. We want our green line to be very big, because big green line means big money. We like money. Okay, so we want to find the place where the green line is the biggest. I don't know, it looks like it happens somewhere in this region. So let's see here. 530. It's like way over here. That's right out. Q equals 170 and Q equals 530. That's right out because C is right out. Q equals 170. That's that looks like this point right here. That looks like it could be a break-even point. So that's definitely not it. And Q equals 400. Yeah, that's in our region. So A is our answer for sure. Okay, so that's how we do that one. So, okay, we have the graph of f of x given below. And we're supposed to pick out which one is the graph of f prime of x. Okay, so what do I see? I see a function which is increasing until we hit this point here. And then we're decreasing for a while. And then after we hit this point here, that's another turnaround point, and we're increasing after that. So we have an increasing function where f prime should be larger than 0, and then we should have a period where f prime is less than 0, and then we should have a period where f prime is again larger than 0. Well, in the first picture here, we're less than 0, then greater than 0, and then less than 0, which is the polar opposite of what we want. The second one, we've got greater than 0, then less than 0, and then greater than 0. So that one's going to be it for sure, but let's check the other ones. Less than 0, then greater than 0, or greater than 0, and then less than 0. Yeah, those are going to be right out. Okay, so really I just decided from looking at the parts of f where we are increasing or decreasing, that should tell us what the sign of f prime is. And if f prime is larger than 0, then you better believe that the value of the function f prime should lie above the x-axis. Okay, so that's because, so let's see, where is that? That's negative 2. So let's make this really concrete here. At the point negative 2, the tangent line has a positive slope. It is an increasing function, which means that at -2, we should have that the height of the derivative should be above the x-axis. Then, at the point 0, our tangent line is decreasing. Therefore, at the point 0, our derivative should lie beneath the x-axis, and it does. Then, at +2, we are again having an increasing tangent line. Okay, well, it's not the best tangent line ever, but you get the point. It's increasing. So at 2, again, the value of our function should lie above the x-axis. Okay, another one here. We have the graph of f of x, it's given below, and we want to decide which is the graph of f double prime of x. So I need to split this graph up into the places where it looks like an n and where it looks like a u. Okay, so in other words, if I'm driving my car along this path, I want to understand, is my steering wheel being turned to the right, or is my steering wheel being turned to the left? Or clockwise, counterclockwise? Well, initially I'm turning to the right, sort of, and then it looks like as I come along here, eventually I sort of even out. And it looks like the point where my steering wheel would be exactly straight would be around this point here. And to the left, this whole thing kind of looks like a piece of an N. And to the right, it kind of looks like a piece of a U. Okay, so that's going to be my inflection point where my concavity changes. And to the left, we're concave down, so it should be less than 0. And to the right, we're concave up, so f double prime should be larger than 0. So we should have a graph of a function which is initially less than 0, and then later larger than 0. So B and A are right out because, well, they go from being negative to negative, or from being positive to positive, but we only have one inflection point. So we should choose C or D, and we should choose the one which corresponds properly to the concavity. It should be less than 0 initially, and then as we move to the right, we should go through the x-axis and then be larger than 0. That's corresponding to C. Okay. Last one. We're not going to do that bonus. Oh, we're not going to do any of the bonus, actually. Okay. I want to find this integral from 2 to 8 of x squared plus all this jazz. Do the integral from 2 to 8 of x squared minus 5x plus 1 dx should be x cubed over 3 minus 5x squared over 2 plus x, and we should evaluate this at 2 and 8 using the fundamental theorem of calculus. We plug in 8, we get 64/3 minus 5 times, no wait, 8 cubed. Oh my god, this is going to be painful. Eight cubed. We get 512 over 3 minus 5 times 64 over 2 plus 8. And we will subtract from that the number that we get when we plug in 2. That'll be 8/3 minus 5 times 4 is 20 over 2 plus 2. So, geez, 512 divided by 3. Oh, it's not an even number. Okay, that's annoying. Okay, so this will be 170.666 minus 5 times 32. And we'll add 8 to that. I'm getting 18.667 minus 8/3 minus 10 plus 2 minus negative 5.333. So we will negate that and add it to 18.667. And we're going to get 24.000. Wonderful. So we got A. So that's how we do that problem. We just use the fundamental theorem of calculus. So number 20, we want to find the total area between this curve f of x equals x squared minus 5x plus 1 and the x-axis between x equals 2 and x equals 8. Okay. So this was the work for 19. Now the work for 20. So x squared minus 5x plus 1 between x equals 2, x equals 8. So this could be factored, by the way, as x minus 2 and x plus 3, I think. Yeah, so x minus 2 and x plus 3, so it looks like a parabola with roots at negative 2, no, positive 2, and negative 3. Hang on, something's not right here. What am I doing? Plus 1 is not correct. What does this thing look like? X equals negative 5 plus or minus the square root of b squared is 25 minus 4 all over negative b plus or minus the square root of b squared, that's 25, minus 4ac is 4 times 1 times 1 is 4, divided by 2a. So 5 plus or minus the square root of 21 over 2. So let's take 5 plus, let's take the square root of 21. And add 5 to it and divide by 2. Oh, this is gonna be, something's not right here. Is this for real? Wow, it is for real. Okay, so this is something like, these numbers are 4.7912 dot dot dot, and then the one where we subtract would be square root 21, and then we would take 5 minus that, and then we would divide that by 2. So the roots of this parabola are 0.208712153, and this other number 4.7912. So this is going to be a parabola with a root at this decimal point here and this decimal point here, and we have our integral goes from x equals 2 to x equals 8. And what we're supposed to do is find out what is the total area which is trapped between this function and the x-axis between these two bounds. So, in particular, this is the point 4.7912. Why don't we write it in its other form? We'll write 5 plus square root 21 all divided by 2. So what we should really be doing here should be, we should take the integral from 2 to 5 plus the square root of 21 all divided by 2 and make that negative, because that otherwise would give us a negative number which represents the negation of the area underneath the x-axis. So this number here minus 5x plus 1 dx plus, and then we should add to this the integral from 5 plus the square root of 21 all over 2 to 8 of the same thing. So 1 dx. So, all right, let me plug this into a calculator because I don't want to do it. X squared minus 5x plus 1 dx plus integral from that number to 8 of the same function. Let's see what we get. Okay, so if you go through and use the fundamental theorem of calculus on both of these integrals and add up their numbers, you will get d. So this is just to illustrate that the integral does not exactly tell you the total area between the function and the x-axis. If the function passes beneath the x-axis, then it's going to count some of that area as sort of negative area. So there's a difference between this, what we got for 19 and what we got for 20 are not the same. Okay? So at the very least, if you are able to test a few points of this function and realize that sometimes it's beneath the x-axis and sometimes it's above the x-axis, you should know that it's probably not going to be exactly the same between these two. So at a bare minimum, you should be able to rule out 24. You should also be able to rule out -10 because area is always positive, so you can get rid of that one. So I guess that really narrows it down to C and D, and you're going to have to go through this painful computational exercise of plugging in these awful numbers in order to actually get your answer. Okay, so now we are doing 21, which is an antiderivative of x to the -1st power. Well, x to the -1st power is 1 over x. If you write it like that, I think it's easier to recognize that C should be our answer here. Okay. Derivative of ln is 1 over x. All right, for a function, capital F of t and its derivative capital F prime of t, we have integral from a to b of capital F prime of t is equal to capital F prime of b minus capital F prime of a, and we're supposed to say whether this is a true or false statement, and it is mega false. Here's why. We should not have these primes here. It's true that this is equal to capital F of b minus capital F of a. That is what the fundamental theorem of calculus says. Okay, finally, another true-false question. If f of x is increasing on the interval 1 to 7, then the global maximum of f on this interval occurs at x equals 7. Well, let's draw a picture. We have 1 and 7, and we have a function. We don't know its values, but we know that it's increasing on the entire interval, so it's generally going up the whole time. It might look like a line, which is going up, or it could look something like, it could be curvy, but at no point should it go down. Okay, it's increasing. And from drawing the picture, I think it's going to be relatively clear that if we have a function which is going up, then the global maximum on the interval from 1 to 7 is going to occur at the right-hand side of the interval, because the more further to the right we go, the higher our function rises, and so there's really no other place where it could occur. Because if, for example, we had a function which looked like this pink guy, where the maximum occurred at some point which was in the middle, then we would have to be able to say that this point down here was, at the end, was smaller than a point before it, in which case the function had to have been decreasing for a time period, and you can see right here where it is decreasing. So that's really not an option for our picture. So I'm going to say this is a true statement. Global maximum of f on this interval should occur at x equals 7. Okay, so that's it for this review or practice final. Yeah, if you do have any questions about anything, please do send me an email. I think I will probably record my office hours from Friday and post them to the YouTube channel. So if anybody comes to the office hours, I will record those and post them to the YouTube channel so that you can take a look at some of those extra review problems that we do during office hours on Friday at your leisure. So that's the plan. If you want to meet with me virtually to talk over anything at all, please do send me an email. My schedule is relatively open this week for meeting with students, so if you need to meet, please let me know and I can get you some help. So yeah, I guess for now, that's it. Thanks for watching, thanks for taking the class, and good luck on the final.